permutations. We said we take 4 things 3 at a time. So 4 things 3 at a time means I have like 4 possible things to choose from. But I only want 3 positions. So how many do you have to choose from first off? 4, then 3, then 2. Let's There's only 1 left. So let's make this be 2 right now, because I want you to see a difference. So 4 times 3, 2 positions, right? This, we multiply it, becomes 12. You can put this in your calculator, and you guys can always use your calculator. So that's not an issue with your calculator. You're going to put the 4 in first. You're going to go to math. You're going to go to probability. And you're going to come down to your NPR and then put your 2 in. And you'll get your answer. And you can always use your calculators for this. Now, their way they use the formula is this. So here's the 4, here's the 2. The 4 is the n. They say 4 factorial over 4 minus 2 factorial. So it goes like this. 4, 3, 2, 1 over 4 minus 2 is 2. 2 factorial, 2 times 1, and these get crossed out. So to me, they take the long way to do this. Isn't it the same as 4 times 3? So don't use this setup if you're going to figure it out by yourselves. Don't use this, use mine. I do combinations differently than they do too. I'm sure there's a reason to do this, but it works just like that, like this much better. And don't forget you have your calculator. So if we have something like P83, this means make 3 positions and start at 8. 8, 7, 6, and multiply them. They say 8 factorial over 8 minus 3, which is 5 factorial. So 8, 7, 6, 5, 4, 3, 2, 1 over 5, 4, 3, 2, 1. Won't these come out? You get the same exact thing. So if you use one, use mine. So we need to find, using permutations, find the number of ways of forming 4-digit codes in which no digit is repeated. So there's no repetition. If I use a 9, I can't use it again. So I'm using the digits 0 through 9, I'm assuming, because I can have a 0 in there, right? And I need to find 4 digits. This is the best way to work this out. Put the 4 lines there. How many choices do I have for the first one? 10. If I use a 9, how many choices do I have for the next one? 9, then 8, then 7. And you multiply them. How do I write this as a permutation? 10, 4. Okay? Use the lines. It's a lot easier. I'm somewhere around 180 something, I think. Oh, sorry, I'll find it. 169. Well, around 169. Okay, so now, try this next one. I want you to see if you can set up this one. Does order matter? In this case, a psychologist shows a list of 8 activities to a subject in an experiment. How many ways can a subject pick a first, a second, and a third activity? Well, in this case, order matters, because they want them to be a first one, a second one, a third one. If it was order didn't matter, he would say pick 3 activities. But if they specify like this, a placing, a positioning, then it's order matters. Then it's a permutation. That's a good way to tell. It used to be, we used to look for the word different ways, things like that. How many different ways, how many different lineups, how many different arrangements. but they also use that in combination sometimes. So try that. Try to set it up with using a P and the lines underneath it. How many lines are you going to make? 3. Because you want first, second, third. How many ways do you have to choose the first one? 8. Then what? Times 7 times 6. Good. So this is P what? 8, 3. Could I use 8 factorial? No. Because 8 factorial means I'm going to line up all 8. Okay? I only wanted 3 positions. So I can't use 8 factorial. Okay? I like laying out the lines. I think it helps. 43 race cars started the 2013 Daytona 500. You'll be amazed at how many ways this can happen. In how many ways can the cars finish first, second, and third? So is there a difference between finishing first and second and third? So definitely order matters. When we say order matters, we automatically know we have a permutation. So imagine P 43, 3, 43, 42, 41. What'd you get, Chris?
74,046.
74,046. That's a lot of different ways that they can finish first, second, and third. A lot of different ways. Who would think that? Who would think that, right? Okay. A board of directors of a company has 12 members. One member is the president, and another member is the vice president. Another is the secretary, and another is the treasurer. So how many positions do they want to fill? 4. And do they make a difference what positions they go in? Tori says, I don't want to be secretary, I want to be president. So we've got 4 positions. Order matters. If it helps, do this. President, vice president, secretary, treasurer. How many people do you have to choose from? 12. So what? Pick one. So I can't pick the same person for president and vice president, right? So that's why we drop down, drop down, drop down. So this is P, 12 things, 4 at a time. And that also is a fairly nice number. That number is 11,880 ways. So you think you're only working with 12 people, and you need to only pick 4 positions. But look at all the different ways you can take those positions. Those numbers still blow me over. Okay, let's hit distinguishable permutations today, and then we'll be done with our permutations. Distinguishable, and you might recognize this from the regions, like I did the word idiot yesterday, the 2 I's. You got to take out the duplicates. So what we're going to do here is, and we're not going to use their formula, we're going to use mine. A building contractor is planning to develop a subdivision. The subdivision is to consist of 6 one-story houses, 4 two-story houses, and 2 split-level houses. How many houses altogether are they putting here? 12 houses altogether. Now the problem is this. How many distinguishable ways can houses be arranged? In other words, if I put 2 one-story houses together, and then 2 four-story houses together, and then like build them like this, I can't interchange my 2 one-stories. They'll look exactly the same, right? So distinguishable means I got to take out the duplicates. So I start with my top number, 12 factorial, and I have to take out the duplicates. This is a really hard one to see. I like the one with the letters better. But you have to tell yourself this. You have 6 factorial, 4 factorial, and 2 factorial. I really think it would be a better example than this. The other one is also planning trees. Okay, so you're going to have to take your duplicates out. We'll do this in a minute with words in it. 6 factorial, they duplicate. 4 factorial, 2 factorial. Now, the problem with your calculator is this. If you put this in your calculator, this has to have parentheses around it, unless you use your fraction key. If you use your fraction key, that's fine. Otherwise, you need parentheses. Let's say a word like Mississippi. I think it works better for you to see with letters in it. How many letters in Mississippi? 11 letters. Find me how many duplicate letters there are. How many I's, how many S's. Hello, Mrs. Horn. Hi, good, how are you? Sure. Okay, thanks. Mike, when the bell rings, to attendance, Mr. Jones. How many I's do we see? 4 I's. What else repeats? 4 S's. And what? And 2 P's. So if I rearrange this word and I rearrange these 2 I's, I'm still going to look exactly the same, right? I got to take out my duplicates. So I write down which ones repeat, just like we did up here. It's just harder to see what the house is because you really can't visualize that. And then just take this out. 4 factorial, 4 factorial, 2 factorial. So we had 11 factorial over 4 factorial, 4 factorial, 2 factorial. Does that make more sense? I mean, it's probably hard to visualize the houses, but, and then they do another one with trees. But it works the same process. If you have things that repeat that are exactly the same, if you switch those, nobody noticed that. So that's why they call these distinguishable permutations. Okay, let's try their last one, even though this is, I think, a shrubbery one. The contractor wants to plant 6 oak trees and start like this. 6 oak trees, 9 maple trees, 5 poplar trees along the subdivision. The trees are to be spaced evenly apart. How many distinguishable ways? Like if you put 3 oak trees and then 3 poplar trees, if you switches the oak trees around, you wouldn't notice it, right? Because they're still all oak trees. So these are what they mean by distinguishable. How many total trees is he putting in? 20 trees altogether. So you start with your 20 factorial, and you take out your duplicates. My 6 oaks, you can't tell the difference between my oaks. 6 factorial. My 9 maples, 9 factorial, 5 factorial. Okay, and then you calculate that. Does that make sense? It's a little harder to visualize with these. I think it's easier to visualize when you have like a word, because you can actually see the duplicates yourself. Okay, so tomorrow we'll start with combinations. We'll go on and look at, I love